So welcome to the class. Solution: vapor pressure of liquid solutions. Liquid solutions are formed when solvent is a liquid. The solute can be a gas, a liquid, or a solid. Solutions of gases in liquids have already been discussed in section 2.3.2. In this section, we shall discuss the solutions of liquids and solids in liquids. Such a solution may contain one or more volatile components. Generally, the liquid solvent is volatile. The solute may or may not be volatile. We shall discuss the properties of only binary solution, that is, the solution containing the two components, namely the solutions of one liquids in liquids and solids in liquids. Vapor pressure of liquid to liquid solution. Let us consider a binary solution of two volatile liquids and denote the two components as 1 and 2. When taken in a closed vessel, both the components would evaporate and eventually an equilibrium would be established between vapor phase and the liquid phase. Let the total vapor pressure at this stage be P total and the P1 and P2 be the partial vapor pressure of the two components 1 and 2 respectively. These partial pressures are related to the mole fractions x1 and x2 of the two components 1 and 2 respectively. The French chemist Francois Martin-Raoult in 1886 gave the quantitative relationship between them. The relationship is known as the Raoult's law, which states that for a solution of a volatile liquid, the partial vapor pressure of each component of the solution is directly proportional to the mole fraction present in the solution. Thus, for component 1, P1 is directly proportional to the x1 and P1 is equal to P1 naught x1, where P1 naught is the vapor pressure of the pure component 1 at the same temperature. Similarly, for component 2, P2 equals to P2 naught x2, where P2 naught represents the vapor pressure of the pure component 2. P total over the solution phase in the container will be the sum of partial pressures of the components of solution and is given as P total equals to P1 plus P2. Substituting the values of P1 and P2, we get P total equals to x1 P1 naught plus x2 P1 naught equals to 1 minus x2 P1 naught plus x2 P naught 2.15 equals to P1 naught plus P2 naught minus P1 naught x2 2.16. Following conclusions can be drawn from the equation 2.16. Total vapor pressure over the solution can be related to the mole fraction of any one component. 2. Total vapor pressure over the solution varies linearly with the mole fraction of the component 2. 3. Depending on the vapor pressures of the pure components 1 and 2, total vapor pressure over the solution decreases or increases with the increase of the mole fraction of the component 1. A plot of P1 or P2 versus the mole fractions x1 and x2 for a solution gives a linear plot as shown in figure 2.23. Figure 2.3 shows the plot of a vapor pressure and the mole fraction of an ideal solution at constant temperature. The dashed lines 1 and 2 represent the partial pressure of the components. It can be seen from the plot that P1 and P2 are directly proportional to X1 and X2 respectively. The total vapor pressure is given by the line marked 3 in the figure. These lines 1 and 2 pass through the points for which x1 and x2 are equal to unity. Similarly, the plot line 3 of P total versus x2 is also linear. Figure 2.3. The minimum value of P total is P1 naught and the maximum value is P2 naught. Assuming that the component is 1 is less than volatile than component 2, that is P1 naught is lesser than P2 naught. The composition of the vapor phase in the equilibrium with the solution is determined by the partial pressure of the components. If Y1 and Y2 are the mole fractions of the components 1 and 2 respectively in the vapor phase, then using Dalton's law of partial pressure, P1 is equal to Y1 P total and P2 is equal to Y2 P total. In general, Pi is equal to Yi P total. Example 2.5 is given in your book, so please read from the book. Raoult's law as a special case of Henry's law. According to the Raoult's law, the vapor pressure of a volatile component in a given solution is given by Pi is equal to Xi Pi naught. In the solution of a gas in a liquid, one of the components is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry's law, which states that P is equal to Khx. If we compare the equations for Raoult's law and Henry's law, which states Henry's law, it can be seen that the partial pressure of the volatile component or gas is directly proportional to its mole fraction in a solution. Only the proportionality constant Kh differs from Pi naught. Thus, Raoult's law becomes a special case of Henry's law in which Kh becomes equal to P1 naught. Then 2.4.3 Vapor pressure of the solutions of a solids in a liquid. Another important class of solution consists of a solid dissolved in a liquid. For example, the sodium chloride, glucose, urea and cane sugar in water, and iodine and sulfur dissolved in the carbon disulfide. Some physical properties of these solutions are quite different from those of the pure solvents. For example, vapor pressure we have learnt in Unit 5, Class 11 that liquids at a given temperature vaporize, and under equilibrium conditions the pressure exerted by the vapor of the liquid over the liquid phase is called as the vapor pressure. Figure 2.4a. Decrease in the vapor pressure of the solvent on account of the presence of the solute in the solvent. A. Evaporation of the molecules of the solvent from its surface is denoted by the blue dot. B. In the solution, solute particles have been denoted by the green, and they also occupy part of the surface area. This is shown in figure 2.4. In a pure liquid, the entire surface is occupied by the molecules of the liquid. If a non-volatile solid is added to a solvent to give a solution, the vapor pressure of the solution is solely from the solvent alone. This vapor pressure of the solution is given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. In the solutions, the surface has both solute and solvent molecules, thereby the fraction of the surface covered by the solvent molecules gets reduced. Consequently, the number of the solvent molecules escaping from the surface is correspondingly reduced, thus the vapor pressure is also reduced. The decrease in the vapor pressure of the solvent depends on the quantity of a non-volatile solute present in the solution, irrespective of its nature. For example, decrease in the vapor pressure of the water by adding 1.0 mole of sucrose to 1 kg of water is nearly similar to that of produced by adding 1.0 mole of urea to the same quantity of water at the same temperature. Raoult's law in general form can be stated as: for any solution, the partial vapor pressure of each volatile component in solution is directly proportional to its mole fraction. In a binary solution, let us denote the solvent by 1 and solute by 2. When the solute in a non-volatile, only the solvent molecules are present in the vapor phase and contribute to the vapor pressure. Let P1 be the vapor pressure of the solvent, X1 be the mole fraction, and P1 not be its vapor pressure in the pure state. Then according to the Raoult's law, P1 is directly proportional to the X1 and P1 is equal to X1 P1 naught. 2.20 The proportionality constant is equal to the vapor pressure of the pure solvent P1 naught. A plot between the vapor pressure and the mole fraction of the solvent is linear, that is shown in figure 2.5. Figure 2.5 shows that if a solution obeys Raoult's law for all vapor pressure concentration, its vapor pressure would vary linearly from 0 to the vapor pressure of the pure solvents. Then 2.5 Ideal and non-ideal solutions. Liquid solutions can be classified into ideal and non-ideal solutions on the basis of the Raoult's law. 2.5.1 Ideal